A very good day. Today, we are from Group C14 and I will present to you our lab report on radial heat conduction in a brass disc. So the test procedures are as follows. Firstly, the water tap is opened slightly to provide cooling for the brass disc device. Next, the power supply unit is switched on and is adjusted to 10 watts, 30 watts, and 15 watts. The system is left to cool down for a couple of minutes so that to ensure that the disc achieve thermal equilibrium. The clip is connected to the first thermistor temperature sensor point and the pin is properly inserted into the socket. The temperature value for T1 until T6 is read and recorded. The steps are repeated for 30 watts and 15 watts. Finally, the power supply is adjusted to 0 and unit switch is turned off and the water tap is closed. Our results show a clear downward slope trend. As the radial distance increases, the temperature decreases as you see in the temperature versus radial distance graph. This can be attributed to the increase in the cross-sectional area resulting in a less concentrated heat in the periphery. From the temperature difference versus the natural log of the radius, we found a linear relationship for all of the power inputs, which validates the theoretical inverse algorithmic profile expected for a radial conduction. Using Fourier's law, we are able to calculate both the experimental and theoretical thermal conductivity of the brass. While these values were close to theoretical expectations, we noticed a consistent trend, where the experimental thermal conductivity decreased as the power input and thus this temperature increased. Now let's discuss a key finding. Why did the thermal conductivity of our brass decreases as we increase the power? In metals like brass, heat is primarily moved by free electrons. As the temperature rises, the metal's atomic lattices vibrate more vigorously. These increased vibration act as obstacles, causing electron scattering and more frequent collisions. This reduces the mean free path of the electrons, making heat transfer less efficient. Our results confirm that the thermal conductivity is not a fixed constant. It is a temperature-dependent property that varies based on the thermal energy of the material. Finally, we will address the experimental errors. Minor deviations were caused by the power fluctuations in the device itself and some heat loss to the surrounding despite the air gap and heat-resistant casing. To improve accuracy of our experiment, we can do data averaging and perform the experiment in a more controlled environment to minimize convective losses. That's all from us. Thank you.